part 1 of section 6.3, Parametric Equations and Motions. So this is sort of a review. We did parametric equations in chapter 1, but we're going to do them in a little more detail in this chapter, and we're also going to connect them to vectors. So let's start by reviewing what the definition of a parametric equation is and how we go about using them. So first, a parametric curve is a graph of ordered pairs and of course our ordered pairs are x comma y, where each of those ordered pairs is defined as a function of a third variable. So where x equals f of t and y equals g of t, and it's on an interval. It's possible that t is not defined for every value, so we'll restrict the interval sometimes. So what are those parametric equations? So we have two of them, x equals f of t and y equals I did that up here too. Oh no, I did it correctly there. G of t. So these are the equations in terms of x used to define a two-dimensional vector, which is something we did not discuss in chapter 1. Okay, parameterization, what that is the defining of the curve on an interval of t values. So that's when we take a rectangular equation and turn it into a set of equations, or parametric equations, defined in terms of a third variable. So the defining of a curve on an interval of t values. Okay, so let's work with some of these types of equations. So the first set has to do with reviewing how to graph these. So this is number 7 on page 482, and the directions for that section give you a set of parametric equations, x equals 3 minus t squared and y equals 2t, and we are to graph this set of parametric equations using a standard viewing window. And for number 7, they want us to use t values between 0 and 10. So I didn't make a table for all of those because I didn't think we needed to write them all out. So I'm just going to do 0, 2, 4, 6, 8. And I actually want to put the last one on here. So let me add one more row. I didn't realize I shorted myself a row. So this will be 10. So filling in my x and y values by substituting these t values first into x equals 3 minus t squared, and then secondly into y equals 2t. I can fill in my table to get my ordered pairs, and then I can graph them. So x, you put 0 in, you get 3. You put 2 in, you get -1. Substitute 4, you get -13, and so on. And these numbers are going to be off of our window, but we'll work with them. So you can see that as t gets larger, x is getting a lot smaller. And then for y, doing the same thing, substituting the t values into y equals 2t, we get 0, 4, 8, 12, 16, and 20. So graphing the points that we can, that we're going to be graphing this set of points here, our XY pairs. So we're going to have 3, 0. Then we have negative 1, 4. And then we have negative 13, 8. So I'm going to kind of guess where that is. And I can't graph the rest of them. But it's going to look like that. It's going to go in that direction. So that's number 7. Okay, next, how do we eliminate the parameter? What does that mean? Sometimes we may not want t in there, especially if we're looking at the behavior of the function. Sometimes we do want it there because we want to break it into what's happening in each direction, the horizontal and vertical. But at other times, we want to just see what's going on with the curve as a whole. So we eliminate the parameter to obtain a rectangular equation in X and Y that represents the curve Okay, so our next set of examples is going to be all about doing that. So page 482, exercises 11 through 26, asks us to use an algebraic method to eliminate the parameter and identify the graph. And then if you want, you can put in your graphing calculator to make sure that you have the correct graph. So for number 11, we were given this set of parametric equations, x equals 1 plus t, and y equals t. Now, ones like this are pretty straightforward. Since y is already solved for t, I'm going to go ahead and substitute that t here and then solve for y. So this one's pretty straightforward. So I'm going to put in x equals 1 plus y, replacing t with y, and then solving for y, you get x minus 1 equals y. So it's easy to see that this is a line through the points 1, 0, and 0, negative 1. Now to check that on the graphing calculator, so let me pull up the 84. So I'm going to change my mode to parametric. So while I'm here in rectangular, let me go ahead and put in my equation so we can compare it to it. X minus 1, and I'll hit zoom 6. So there's the line. So if we put this in parametric mode, so we'll go down, go over to parametric, and now I'll go under y equals, whoops, I guess I didn't do it. Thought I hit enter, there we go. So now when I go under y equals, what you're going to do is you're going to have two equations for each one. You have an x equation and y equation. So I'm going to put 1 plus t in, and when you press the variable button in the 84, the t will automatically come up. And for y, I press just t, and then you definitely want to look at your Windows settings. You want a very small t step. This is pretty good. There's your standard viewing window there. That's usually what you get. You get 2 pi for a t max. And so now when I hit graph, what I'm only going to have here is this part of the graph because I didn't catch something in my window. oh, my t max is going from 0, so I need to go a little further because I can have negative t values in this. So if I do like a negative 6, just to make it simple. There we go. Okay, so we know it matched. Now we're going to do it on the Inspire. So you're going to pull up a graph page. And I'm not going to regraph the rectangular one, but to get parametric, you hit Menu, and then you go to 3, Graph or Edit, and all the different types of equations are there. And we're going to choose parametric, and then we're going to put in 1 plus t. And then for y, we're going to put t in. And let's change our step. It's right here, which is nice. So let's do -6 like we did on the other one. And then you hit enter, and there's the line. So you can see it does match, that it is correct. Okay, so number 15, our equations are now x equals t squared and y equals t plus 1. Now this one's a little more tricky because you have your x has the t squared. So I'm going to go ahead and solve the y again for t. So I get y minus 1 equals t, and then I'll substitute the y minus 1 in for t squared. So I'm going to have x is going to equal y minus 1 squared, and honestly, just leave it that way. It's a bear to get by itself. I mean, if you want, you can take the square root of x. Don't expand the y minus 1, because then you have a y squared and a y. And it's going to be plus or minus. This will be y minus 1, so you have 1 plus or minus the square root of x. And really, even from here, what you can say is you have a parabola that opens right with a vertex of 1, 0. And you can double check that on your graphing calculator. All right, number 23 is a different type of problem, and this is going to tie in our trig. So now we're going to have x equals 5 cosine t and y equals 5 sine t. Now, you might say, oh great, I have to use inverse trig, and then I'm going to have a mess, and how do I really get rid of the t, and what is that going to look like? The thing is, there are little tricks with trig, and that's why we spend a lot of time on our identities. When you see cosine and sine together, the best thing to do is to create a Pythagorean identity. So if I'm to square both of these, I would have 5 cosine t squared plus 5 sine t squared. So I've created x squared plus y squared, and I have 25 cosine squared t plus 25 sine squared t. And hopefully a lot of you see where we're going with this. So I can factor out a 25. And if you didn't see it, hopefully you see it now. I now have my Pythagorean identity, which equals 1. So x squared plus y squared equals 25. And what I've created is a circle. That's the equation for a circle, centered at 0, 0, with a radius of 5. And we're going to get into this more in the next section when we start talking about a different type of graph, which are polar coordinates, how we can use sine and cosine to create circles. So we're going to start the second part of the video with exercise 27, and we'll finish in that part.